Welcome to Brain Vision.
Okay, so we're doing chapter 37, problem 92 here. So it says light of wavelength 424 nanometers falls on a metal which has a work function of 2.28 electron volts. Part A asks how much voltage should be applied to bring the current down to zero. Okay, so we're going to use equation 37 4b to calculate the maximum kinetic energy. And if we set that equal to the product of the stopping voltage and the electron charge, then that's going to be the voltage that we need to apply to completely stop this. So how that looks like is we have Kmax here, and we set this equal to the photon energy hf minus the work function, and this must equal E times V naught, which is our potential difference or our voltage. If we rearrange that, we can solve for V naught as hf minus the work function over E, and this also can be written in terms of the wavelengths, such as hc over lambda minus the work function all over E. So now let's figure this out. So we have 1240 eV nanometers divided by 424 nanometers minus the work function 2.28 eV, all divided by E. Well, this comes out to being 0.65 eV over E. So these E's just cancel out and we have 0.65 volts. Cool. Let's move on to part B now. Part B asks, what is the maximum speed of the electrons? Well, first we're going to use the non-relativistic kinetic energy equation, set Kmax equal to 1/2 mv squared. So this, as long as the velocity we get out of this is significantly lower than the speed of light, then we can use this classical equation. If it's closer to the speed of light, we're going to have to go back and update this with the relativistic equation. But let's rearrange this for V, and we get V is the square root of 2k max over m. So we can solve this for the speed, and we'll get 2 times 0.65 eV over 9.11 times 10 to the negative 31 kilograms. And to keep everything in SI units, let's convert this EV to joules by multiplying 1.6 times 10 to the negative 19 joules per EV. Cool, so we can plug this in, and since we're in SI units, we get an answer out 4.8 times 10 to the 5 meters per second. And this is quite a bit lower, less than 1% of the speed of light, so we can know that our classical approximations is good. Awesome. So lastly, we have part C. It says, what is the de Broglie wavelength of these electrons? Well, lambda here, the de Broglie wavelength is just h over p, which is h over mv. So we can plug that in. 6.63 times 10 to the negative 34 joule seconds over 9.11 times 10 to the negative 31 kilograms times 4.8 times 10 to the 5 meters per second. Awesome. If we plug all this in, we get an answer out. Let's check that we're in SI units. Yes, yes, and yes. So our answer comes out to being 1.52 times 10 to the negative 9 meters, or 1.52 nanometers. Cool. There's the answers for everything.